Okay, so let's see the problem in the question in section 5.3. Yeah, and I think you could check it by the solution. I have already posted you the in our line group for its solution. Okay, so I just give you a, since you have solution, I just give you a quick explanation, a quick explanation again. Yeah. Actually, we have already talked about these two questions in class for another examples. Okay, so first of all, we want to find a least square solution to a linear system, And for this linear system, as we know in chapter 1, if we want to solve it, we will consider its augmenting matrix, or you could say coefficient matrix firstly. 1, 1, 1, 1, negative 1, 2, and we let x be x1, x2, and then let the vector b be this one, 3, 1, 0, 3, 1, 0. So if you want to solve this linear system, it means that when you consider its multiplication, you will see this part is exactly our ax. It's exactly our ax, right? So here 1 times x1 plus x1 times x2 is exactly this one. And 1 times x1 subtract 1 times x2 is exactly this one. 1 times x1 plus 2 times x2 is exactly this one. And 310 is this one. 310 is this one. So this linear system also means that A is equals B. A is equals B. And if we want to solve this linear system, originally we will consider this one. I mean, originally we consider AB, we consider augmenting matrix AB, right? So it's 1, 1, 1, negative 1, 1, 2, 3, 1, 0. And we multiply negative 1A to the third row, second row. So it's 1, 1, 3, 0, 0. And here 1 subtract 1, 0, negative 1 subtract 1, negative 2, 1 subtract 3, negative 2, 1 subtract 1, 0, 2 subtract 1, 1, 0 subtract 3, negative 3, here. So here multiply by 2A to the second row. So 0, 1, negative 3, 1, 1, 3 here is 0, 2 subtract 2, 0, subtract 6, subtract 2, subtract 8. So you see, you will have this row. This row means that 0 times x1 plus 0 times x2 equals negative 8. But it's a contradiction. We don't have any solution x1, x2 such that this equation holds. So actually for this linear system, it's inconsistent. It doesn't have any solution. So now our question is that to find the least square solution, not the exact solution, since actually they have no solution. But we want to find the least square solution. So find the least square solution, as we say, actually we should consider A transpose. So A transpose means that first column becomes first row, second column becomes second row. And then now we consider the problem A transpose A equals A transpose B. Sorry, this one. We want to, so now it becomes this one. We want to solve this equation A transpose B. We want to solve this equation. So of course you should know A transpose A and the matrix A transpose A and the vector A transpose B. Okay, so A transpose A is exactly here. It's just some computation. I think just some computation. So A transpose A is 1 plus 1 plus 1, 3. And here is 1 subtract 1 plus 2. 1 subtract 1 plus 2. 1 plus 1 plus 4, so it's 6. And the A transpose B is exactly 3 plus 1 plus 0, 3 plus 1, 4. 3 subtract 1, 2. Yeah, 4, 2. This one. So our new matrix is this one. New vector is this one. We want to solve this one. So now just consider the augmenting matrix to solve it. just consider augmenting matrix to solve it. 3, 2, 2, 6, 4, 2, 4, 2. Yeah, and apply elementary law operation, we could solve it. So here there are several ways to solve it, and here both all of them have the common number 2, so we could multiply 1 here. So it's 1, 3, 1, 3, 2, 4 here. And we could use this guy to cancel. Yeah, for original we could interchange 2 rows. So here is 1, 3, 1, 3, 2, 4. And now multiply by negative 3a to the last row. So it's 1, 3, 1. So it's 0. 2 subtract 9. So it's negative 7. 4 subtract 3 is 1. It's 1. And multiply by negative 1 over 7. So it's 0, 1, negative 1 over 7, 1, 3, 1. 1, 3, 1. Yeah, here is just some computation. So let's see, the final solution is 1, 0, 10 over 7. 10 over 7. Okay, so this vector 10 over 7, negative 1 over 7. This new vector. So this vector here is our A transpose A, A transpose B, and here is identity 2. So it means that actually we could in the process it means that we could multiply by A transpose A inverse in both sides. A transpose A, their inverse. So here it becomes identity, and here is what we want. And actually this vector is this one, A transpose A inverse times A transpose B. This one, it's exactly this vector. Yeah, and it's exactly what we want. This square solution. It's our x1, it's our x2. It's our x1, it's our x1 and x2. X1 and x2. Okay, so it's the first question. And the second question is related to first one. Okay, so now I explain some. Okay, are you ready? Okay, so for second question, we have a given data A, B, and it's a pair when A equal, given data, the pair is when A equals 1, then B equals 3. When A equals negative 1, B equals 1. When A equals 2, B equals 0. Right? And we want to find a straight line, a linear function, such that for this linear function, it best fits the given data. So the function what we want to figure out is this one. I mean y equals c1 times plus c2x. Okay, so I explain how to connect these two questions. The function is here. This function is what we want, but we don't know the c1, c2. So we want to figure out the constant c1, c2. So if we let x be, and for the data we have three. For the data we have three pairs. And then the first one is our x, is our y. So the first one has x equals 1. Then if you plug in the function, we call it L. For this linear function, if we plug in the value 1, you will get y equals c1 plus c2 times 1. Here I use the rectangle 1, you will get this one. And if let x be negative 1, if you let x be negative 1, you will get the y value equals c1 plus c2 times negative 1. And then we have the third pair, x equals 2. Then the y value for this function if you want to plug in the three x values, then the corresponding y values in this linear function are the values this guy, and the last one is this one times 2. Yeah. Okay. But for our given data, so here, so for our given data, if x equals 1, x equals -1, x equals 2, its y value is this one. It should be b is 3, b is 1, b is 0. So I mean we want to find the C1, C2 such that their subtraction is the minimum. But what does the subtraction mean? Actually, we consider it. We view it as this way. We have our given is this one. Given data b is 310, and with the function we find is this one. In the linear function, we have the 3 y values. So in the linear function, we have the 3 y values. The first one is C1 plus C2, C1 subtract C2, C1 plus 2C2. So you could view it as a vector, a point in R3 space. So now our question is, we want to minimize their subtraction, their distance. We want to minimize their distance. But here we choose the distance. What does it mean? Square root of all of their square, right? All components their square. Square root of all sum of their square, sum of their each component square. Okay, so I mean, yeah. Let me see. Yeah. So it means that here that if we want to find C1, C2 such that this term is the minimum, such that this one is the minimum. This one is minimum. But if you see, actually if you consider the matrix A, what's this vector? If you consider, if you let A be this matrix, 1, 1, 1. Here, why do we, for the first column, why do we consider this one, 1, 1, 1? Because the coefficient is 1. You could view it as 1, 1, 1. So we put the first coefficient, for the first column, we put the coefficient 1, 1, 1. For the second column, we put the coefficient 1, -2, 1. 1, -2, 1. So 1, -1, 2. 1, -1, 2. 1, -1, 2. And for C1, C2, both of them have C1, C2, and we let X be C1, C2. Then you will see what's their product. Their product is actually AX is actually C1 plus C2, C1 subtract C2, C1 plus 2C2, right? So it means that this term is exactly X. This term is exactly X. This term. And 310 is actually B. So now the question becomes, we want to minimize B subtract X its length. B subtract X its length. And it means that we want to find C1, C2. We want to find C1 such that its length is the minimum. But C1, C2 also means the solution X. It also means the solution X. It also means the solution X, right? Solution X. It also means the solution X. So this question becomes previous question. actually in previous question you could see that if you replace C1 C2 by x1 s2, it's exactly this one. S1 plus s2, S1 subtract s2, S1 plus 2 s2, and the 3 1 0 is actually this one. Here, if you remember that our matrix in this example, A is 1 1 1 1 negative 1 2 in our example, and you will see it's exactly they are the same. Exactly they are the same. So now we just need to use the result in previous example. So now we want to minimize E, and we know that the solution, and by above, by 1, we know that the solution C1 C2, the solution is 10 over 7 negative 1 over 7. It's the solution, it's the least square solution. It's the least square solution, the least square solution. Least square solution. So for our linear function, is this one. Our linear function is this one. C1 is this guy, C2 is negative 1 over 7, and the function is this one. So it's 10 over 7 subtract 1 over 7x. It's the linear function of what we want to figure out. It's the linear function of what we want to figure out. Okay. So now we can see the linear function, and so its degree is 1. We just have constant and the polynomial whose degree is 1. Yeah, these two terms. Yeah. Okay. Yeah. So now I consider. Let me tell you. Okay. So it's a question. Second, for the first question is sub question. Okay. So now let me tell you. The question in section 5.5. Question in 5.5. Since I have given you the solution, so just pre-review. 5.5. Okay, so in question in section 5.5 is we have two vectors. Square root of 8 over 3, negative 1 over 3. 1 over 3. Square root of 8 over 3. We want to show U1, U2 is an orthonormal basis of R2. Okay, so in section 5.5, of course, what you want to know is that what's the orthogonal set, orthogonal set and orthonormal set, orthonormal basis. Some definition you should know, and how to check. And a special matrix or orthogonal matrix is relative to orthonormal set. So actually for this question you could solve it by definition or by orthogonal matrix. Okay, so I mean actually we have a well-known result. Orthogonal. Okay, let me tell you later if we use that result. Okay, so we have two ways to solve it. The first way is by definition, just by definition. So by definition it means that we should show that it's orthogonal basis. So of course it should be orthogonal set in R2, and not just orthogonal. It should be univector. So univector and orthogonal set means that they are orthonormal. Orthonormal set. But here we have two vectors in R2 space. So if they are also orthonormal set, then they are automatically orthonormal basis. Automatically orthonormal basis of R2. Okay, so here orthogonal set means that means that their inner product equals 0 if u1 is not equal to uj. And the unit vectors means that they have the length is 1. The length is 1. And length means square root of the inner product. The inner product. Square root of the inner product. Okay, so just follow the definition. The first way is to follow the definition. So follow the definition. First one check orthogonal set. So u1, u2 so check their inner product. So inner product just pointwise multiplication, right? So it's square root of 8 over 3 times 1 over 3 plus negative 1 over 3 times square root of 8 over 3 is 10. So it's square root of 8 over 9 subtract square root of 8 over 9, so it's 0. It's 0. It's u1, u2. So here we just have two vectors. So even they have, if we have three vectors in our three space, then you could check each pairwise 10. Each pairwise 10 their inner product. They should be 0. They should be 0. And here u2, u1. By definition, we know that it's exactly u1, u2 their inner product. So it's also equals 0. It's also equals 0. So by first one, we know that they are orthogonal. It's an orthogonal set. U1, U2 is an orthogonal set here. Orthogonal set. And the second one, we should show that it's a unit vector. It's a unit vector. So U1 it's inner product, but we should take square root. Take square root. So take square root means take square root. And the U1, their inner product. Their inner product just consider square root of a over 3, negative 1 over 3. Consider their inner product. So you should consider their product. Square root a is square, and 8. 3 is square, 9. Plus negative 1 is square. Okay, I write it down again here. And here is square root of 8 times 3 times square root of 8 times 3 plus. Okay, and here is 9 over square root of 8 over 9 plus 1 over 3. 1 over 9, sorry. So it's 1. It's exactly 1. It's exactly 1. Yeah. And if you check U2 its length, by the similar way, you will see. By the similar way, you will see 1/2, square root of 1/2 is square, so it's 1 over 9. Plus square root of a over 3 is square, so it's a over 3. A over 9, so it's also equal to 1. Also equal to 1. So they are U1, U2 are also unit vector. U1, U2 are also unit vector. So by these two results, we know that U1, U2 is also normal set in R2. Okay, because U1, U2, U1, their inner product equals 0 means that they are orthogonal. U1, U2, they are unit vectors, so they are also normal. And also normal and dimension R2 its dimension is 2, and we have two vectors. So U1, U2 are also normal. Automatically, they are also normal basis of R2. Also normal basis of R2. Then we are done. Okay, then we are done. So it's the first way to solve it. And the second way, for this part, we could use the orthogonal matrix. Orthogonal matrix, Q. If you say Q is orthogonal matrix. If a matrix Q is called orthogonal, it means that Q transpose Q equals identity. Q transpose Q equals identity. So now, and we have a result. The Q, we consider a Q, and for the first column we put a vector U1. For the second column we put a vector U2. And if it's 2 by 2, even n by n is the same. Even n by n is similar. We have the same result. Q, if we denote it by this way, U1, U2 are two vectors in U1, U2 are two vectors in R2. Then what can we have? What can we have? The result say that U1, U2 they are orthogonal, orthonormal. Orthonormal say means that Q transpose Q equals identity. But if it's just orthogonal say, orthogonal, then the result is that Q transpose Q is diagonal. What we have shown is this one in our class. Anyway, so now we will use this result. So just check. So now our matrix Q is, we want to show U1, U2 are orthonormal set. So just consider matrix U. So Q is this one, U1, U2. So U1 is square root of A over 3, negative 1 over 3. 1 over 3 is square root of A over 3. And just consider Q transpose Q. And the Q transpose here is square root of A over 3, 1 over 3, negative 1 over 3, square root of A over 3. So you could check Q transpose Q. You check Q transpose Q. And then once you check Q transpose Q, you will see this one, Q is this one, first column, second column. So it's A over 9. Here is A over 9. And sub plus 1 over 9. This one. And yeah. And the second one is square root of A over 9. Subtract square root of A over 9. This one. And this one, square root of A over 9. Square root of A over 9. Again, subtract square root of A over 9. And the last term is 1 over 9 plus 1 over 9 plus A over 9. So finally it's 1, 0, 0, 1. Finally it's 1, 0, 0, 1. So indeed, it's identity. So indeed it's identity. Q transpose Q is identity, means that Q is orthogonal. Q is orthogonal means that here, our result is that U1, U2 are orthonormal set. Also, U1, U2 are orthonormal set. And dimension is 2, so they are orthonormal basis. Okay. Yeah, so it's the solution about these two problems. Okay.